Now next, we're going to look at beta decay. So a neutron decay, well basically what's happening is that a neutron, which has 0 atomic number and 1 mass number, is decaying into a proton and an electron. Okay. This is essentially what's happening. So the corresponding equation is that we have whatever our original atom was, and it decays. Our atomic number doesn't change because a neutron's turning into a proton, and that's still, the same number of nucleons. But we have one more proton, and then we've got an electron floating around. We could also have a positron and an antiproton being created, in which case we're losing a proton and getting a positron, but the amount of energy, the amount of mass converted to energy is still the same. So let's look at how much mass is converted to energy when we have a beta minus, meaning we get an electron instead of a positron. Beta minus decay of thorium-234, which incidentally was the result of our alpha decay up here. Okay, so thorium-234 is got TH234, atomic number 90, and there's a beta minus decay. Well, then we know that our atomic number increases by 1, our mass number stays the same, and number 91 is what's called protactum, which is a fun, an unusual element. So we have a protactum and an electron. Okay. Now, this electron, let me say something now about Appendix F. The masses in Appendix F are for neutral atoms with that many, are for neutral atoms. So this has lost there's an electron that's been lost here that isn't attached anymore, but the mass given for this includes both of these in its total. We didn't care about that. This was a helium nucleus that was emitted. There are 2 electrons missing, so this mass number is off by the mass of 2 electrons. But we didn't really care because the mass of the mass of what's being emitted is so much larger than the mass of the electrons. Whereas in this case, all that's happening is that an electron is being emitted, and so it's substantial. So for beta decay, we need to consider the mass of the electron involved, whereas for the alpha decay, we don't really need to worry about it. Okay. So, if we consult our table, thorium, well, we already had that number up here. So our 234.043596. So our change in mass is that minus the protactum mass of protactum 234, which is 234.043302, and that is for neutral protactum, so it already includes this electron mass. Those are really close, but so our change in energy, and we only care about the magnitude of that, is 2.94 times 10 to the minus 4th mass units. And so if we know our energy is change in mass times c squared, so that's if we just multiply by 931.5 times that to get that our change in energy is 0.274 mega electron volts. So that's how we deal with beta decay. Now this was actually an issue for a while because this was the energy expected to have the emitted that the emitted electrons should have, but they didn't. The electrons actually had the electron energy is less than this. And that was problematic because that seemed to violate conservation of energy, right? There's some energy floating around that they didn't, they didn't know where it was going. So in 1930, this guy named Wolfgang Pauli, Pauli. If you've done chemistry and looking at atomic structure, you may have heard of the Pauli exclusion principle. It's the same guy. But he proposed that this energy was going into some other particle. So Pauli said missing energy was going to another particle. And because they couldn't detect this particle, they assumed a few things. They assumed that this particle has no charge. They assumed that this particle has very small mass. Yeah, that's it. And there was this particle with no charge and very small mass that was, carrying this remaining energy. And then in 1950, Pauli said this in 1930. 20 years later, they finally observed neutrinos, which were this particle that's floating around, and they account for the missing energy. There was also momentum that was not conserved, but these neutrinos then accounted for the missing energy and momentum. So for beta decay, what's really happening is that the neutron is decaying, and we get a proton, we get an electron, and for the case of getting an electron, there's also this is, for whatever reason, this is the symbol for a neutrino. The bar over it means it's an anti-neutrino. The beta plus decay, whatever. The beta plus decay would give off an antiproton, a positron, and a regular neutrino. And so that took care of the missing energy and momentum in the beta decay. Now the third kind we mentioned was gamma decay, and sometimes when other types of decay occur, an atom can be left in an excited state, where the electrons are excited to higher energy levels, and therefore it can emit a photon. And the energy for that photon comes from the mass lost. The excited state is indicated with an asterisk. So like a gamma ray is emitted, but a gamma ray, it has no mass. So the atomic number and mass number aren't changed. But this was an excited state, and that is indicated with this little asterisk. So this is how gamma decay works. There's a gamma ray that's emitted, and this particle loses energy. And gamma radiation is the most dangerous of the three types. Now, generally speaking, an unstable atom follows a decay series until it winds up being a stable atom, where it undergoes alpha and beta decay repeatedly. At one step sometimes it can take different paths. Like at one step it might only be able to do an alpha decay and then only do a beta decay, but then at some steps it might be able to do one or the other, but then it'll kind of compensate and do the second one later. There's a chart on page 1128, has the decay series for uranium-235. So you can see kind of what that looks like, and it kind of winds its way down until it reaches a stable state.